I'm Nick Pohlman. I'm a professor of mechanical engineering at Northern Illinois College of Engineering and Engineering Technology. I'm here in our fluid mechanics research laboratory. I wanted to talk a little bit today about our wind tunnel, our experimental wind tunnel that we use to test different things about airfoils, about wind velocities and forces, and those sorts of activities. I'm going to play around with a number of devices today, one in which is going to be a Vane Anemometer. I'm going to zoom in a little bit so that you can see that there are little rotating blades that are that measure wind velocity, and so me exhaling into this generates some sort of velocity associated that can be measured by essentially how fast the fan is rotating. What we're going to do in a couple of minutes is we're going to turn on a fan that's on our downstream end of the wind tunnel. That fan is going to pick up air, it's going to consume it, and what's going to occur is all the stuff that is in the upstream to the left is going to take a large area and we're going to reduce it down into a smaller area to increase the velocity. What we do is we take that high velocity and put it into a small test area. So we're going to take a couple of dimensions here and there in order to identify it. Our test area that we have to play with is 18 inches tall and 18 inches wide. And so we're dealing with something that's essentially 1.5 feet by 1.5 feet. Do a little bit of math and that becomes 2.25 square feet of area that our air is going to flow through. So now here we are at the upstream end of the wind tunnel where we can look at what the incoming air is that's going to be drawn into the test section that we just figured out was going to be 2.25 square feet in area. If I take a measurement of our width, it is about 48 inches, so we're going to call that 4 feet to make life a little bit easier. And if you note, it's a square intake. And so if I take something that's 4 feet wide and 4 feet tall, do that multiplication, I have 16 square feet of area of all the air that's going to be coming into the wind tunnel. What we do is we take those 16 square feet and squeeze it into the 2.25 square feet of area, and that ratio, essentially dividing by 8, means that all the air that we draw into this system is then going to be multiplied 8 times, and so the velocity is going to be 8 times more when we get into the test section that we'll go ahead and do some force measurements on momentarily. So let's go back up to the main section and we'll start to turn on the wind tunnel and see what happens to our velocity when we take those comparisons. So now here we are at the very downstream end of the wind tunnel. What we have is a motor controller that we're going to use as a mechanism to drive, and deep down here is a variable speed or an AC motor. That AC motor is just driving at whatever rotation rate we tell it to, that's driving an internal fan in our wind tunnel. Now what will happen is our sound is going to be adjusted because we're going to obviously have a lot more background noise. What I'm going to do is turn on our system. And over time, this is what's called a variable frequency drive. That variable frequency means as I adjust how fast I push the wind tunnel, it's going to adjust essentially the rotation rate of our system. Now because it's a big fan and it has a big mass, it takes a little bit of time to figure out what that speed is going to be. So over time, as you listen in the background, you can identify and hear a bit of a buzz, and that buzz is indicating that we're now going to be drawing air from the intake, all the stuff that we mentioned on the left-hand side, into our test section. And now we're going to compare what is the velocity at the intake, the test section, and then see what we can do to figure out how it messes with the different drag forces in our system. So now, as I mentioned, what we want to figure out is what in the world is happening in terms of wind velocities. And so those wind velocities we need to measure with a tool we're going to call a Vane Anemometer. So if I zoom in closely, you'll see there's a little rotating fan that reads out according to how fast we push air through the system. As I blow into it, we generate some sort of velocity that's measured as a function of how fast the air is moving into the system. Of course, turn it up too fast. Of course, as we watch the wind velocities, we can test how fast the wind is going to go in our test section. So we'll use our little sample opening here. You come in a little bit closer. I'm going to take the Vane Anemometer and put it in the wind speed. Zooming in on the camera, we'll see that it reads out at about 50 miles per hour speed. Essentially the speed that you would be moving at in order to move a vehicle through driving from here to there or to school or something like that. What I also want to do is move to the upstream end of the wind tunnel and show how those velocities compare. So let's go ahead and follow me there. So as I mentioned before, when we had the wind, so no air moving through here, and so now you can hear it's a lot larger area, there's a lot of air being drawn in, and if I take the incoming wind speed, I'll note that the incoming airspeed is about 3.5 to 4 miles per hour. So remember what we talked about, the fact that this area is 16 square feet. I'm compressing it into something that's 1/8 of the size, and so 3 times 8 means that I'm only going to get up to 24 miles per hour. Where's the rest of the velocity come from? Well, it's not quite a direct one-to-one. There's also a density change that's also happening. But we'll leave that one when you get to college sometime in the future. So now what in the world is happening that I've got the test section, that I can put my hand in here and I can feel the force and you can see my sleeve being caught up in that wind, and I've mounted an object. And that object is experiencing, there's a small load cell, what we call a force load cell, that I'm going to measure. And what we have here is we've loaded up the load cell, we've powered it up with 10 or 9 volts of essentially potential energy, and then I'm going to monitor what in the world happens to that load cell as I could go ahead, and of course I can push on it more. As I apply more forces to the system, you see that the load cell is going to increase in speed. What we're going to do over time is we're going to compare some of our data. We can look at things that have those kinds of tapered shapes. Inside there is currently a pyramid, 4 sides, but they're all tapered together. And what we can do is compare it to a conical shape. And so the conical shape still has the same profile, but if I look at it from the end, it has a circular type of shape. Now, of course, a sphere is going to be more uniform on all sides of it, which kind of relates a little bit to why a raindrop appears in its particular shape. A raindrop falls and the bottom part is running into all the air, which makes the bottom part of the raindrop going to appear spherical, but then the top part of it becomes a taper so that raindrop falls with greatest efficiency through the drag and through the air that's going to take place. Of course, we want to measure all of these things. I'm reluctant to want to go ahead and change it as the wind tunnel is active, so I'm going to go ahead and shut it down. We're going to bring it back up to the same speed, but the number I want you to look at right now is this 3.7, or about 0.37 millivolts of measurement currently on our load cell. What we're going to do is I'm going to come back and we're going to compare things that have circular shapes and things that have square shapes, and we're going to see how those forces or how those voltage measurements are going to increase or decrease. Right? It's going to take a little bit of time before it gets back up. Now, what we're doing is we're slowly but surely waiting on the wind tunnel to come back online, and so you see that when there's no wind driving the system, my force, or essentially the millivolts that are being measured by our load cell, is substantially decreased. Now, as we watch this, or when you listen on the camera as it begins to accelerate, and there's not a whole lot of wind moving through there right now, it's going to slowly accelerate, and we're going to watch this number increase over time as the wind continues to be drawn through our wind tunnel, increase in its velocity. What's great about drag forces like this is that people think, well, if I drive faster, I'm going to get to my destination that much sooner, and I'm going to use less fuel. The hard part is that the velocity, or essentially the force that something is feeling, grows as the square of the velocity. So when we save time, we would say in a linear fashion, 5 miles an hour faster is a linear decrease in time. The amount of force is going to be something that's square. So 5 miles an hour faster is 25 times the amount of force that would be necessary because of that scaling on that same mechanism. So now we're bringing our wind tunnel back up to speed. What you'll note is we now have the sphere in here. The sphere, because it has a different shape, it doesn't have the 4 sharp corners that our pyramid did. It has the same cross-sectional area, but because the wind can go around it that much easier, we'll note that the force that we're feeling, you're going to say it's Dr. Pohlman, there's not a big difference between 0.370 millivolts and 0.315 millivolts. No, there's not a great difference, but each one of those incremental differences over a long truck drive is going to add up over time. Which would you rather have? $1 million in one day, or would you rather have $10 billion given to you over 10 years' time? I'd rather have the $10 billion over that long period of time, and so that's the same thing that we're feeling in terms of these small forces accumulated. We're going to go ahead and change out to our square cross-section, and we're going to see what number we end up with in terms of forces. We'll be right back. So here we are now, we're on our third object. We originally started out with our pyramid, that piece that had a square cross-sectional shape, but a tapered orientation to it, and it had a particular drag force associated with it. If you recall, it was 0.37 millivolts of measurement on our drag sensor. When we went to a sphere, the part that's going to allow the air to move around it much more freely, we were moving to a smaller drag force. Well, lo and behold, I've now substituted it for a square cross-section, literally like a box truck driving down a highway. And that box truck might have the same frontal area as our pyramid, but because of the side shapes on it, it's going to create problems. You see it's oscillating, but I also know that the force that I'm feeling, or the translation of force, is substantially larger. It's 0.48 millivolts of force. So that means that there's more force compressing on that load cell. That greater force is just the same thing with a truck. Why would you want to have a narrow shape on the front of the truck with a fairing across the top? It helps eliminate some of those features. So even if I take my hand and put it in front of this in order to deflect the air around it, you can see that I substantially decrease the forces that are taking place on our square front end block. The wind tunnel has provided us a great opportunity to test a number of different features. What we can do is we can test things that are simple shape factors, or we can have other teams that are going to go ahead and try to figure out how would I make a particular airflow. So we have some teams at NIU that are dealing with trying to fly model aircraft. How would I change the cross-sectional shape and the dimensions of our airfoil so that it could fly, have lots of lift, but very little drag? Because obviously drag is a very detrimental thing in order to move something forward into space.